Good morning, and welcome to what will basically be our last lesson of the year and our last new topic. And this topic gives us yet another way to think about functions. We think about what we've done just in this course is we've spent a lot of our time dealing with functions that are more algebraic in nature. Y equals, f of x equals, pretty much standard. You've spent most of your math careers working with those. Of course, we moved into trig functions, but again, we could tend to write them as f of x equals or y equals and so on. We did spend some time working with polar functions, realizing that instead of all the points on a plane being considered as an xy location, we could think of them more in terms of an r theta location. Today, what we do is we move into what's known as parametrics and parametric equations. The idea behind these parametric equations is that ultimately the graph will still end up being the same thing in terms of either x and y, but we're using another variable to get to that point. So let's get into this. To define a parameter, I'm just going to call it a third variable. It could be a fourth or a fifth if we have several equations. We'll just say a third variable used to relate to other variables. And usually the variable is either a t or a theta. And you'll hopefully see why as we go through some of these. Now, this is one of the topics I like to get right to the goals so you really know what we're going to be working with this, because again, we're very limited, just an introduction. We want to be able to graph these functions, either by hand or with a calculator. Talk about a calculator in just a few minutes. We want to be able to write them as parametrics. So if you have a function that's not in terms of parametrics, how can we write it? We'll also eliminate parameters, what that will mean, and then we'll work with some projectile motion problems. I'll split this up into two separate videos, working with these first two goals, and then moving on to the other two. So let's take a look at an example. Here's a case, and I know it's tough to see right in here, but we have a function that's x equals 3t squared and y equals 2t squared, and we want to graph this when t moves from -2 to 2 inclusive. Now, in order to start this, we're going to go back to the most basic way of graphing a function, and that is just to plot points. So I'm just going to make a table. However, the table is going to have an extra column. So I'm just going to have the t, and I'm going to write it more vertically, x and y. Okay, so if I basically want t to be anywhere from -2 to 2, it's going to take on these values. And then I want to find the x and y that goes with it. Well, if t equals -2, that's going to be 4 times 3 is 12. Put a -1 in, that's going to be 3. 0 is 0, 1 is 3, and the other one is 12 again. Y equals 2t, you're just going to double it. It's going to be -4, -2, 0, 2, and 4. So in order to graph this function, I just made up a bunch of numbers. Now I could have chosen fractions. This does not mean that t has to be a whole number, but I might as well start with those nice whole numbers. And now if I want to graph the function, I'm still only graphing the xy's. So the x is going from just, 12 the whole time, and the y is going from -4 to 4. So I'll kind of associate it this way, and this will be 12. So we got 6, we got 3, we got 9. This thing goes down from -4 and +4. So if I do want to graph this function, I just plot the points. 12, -4 is one of them. 3, -2. 0, 0. 3, +2. 12, 4. Now, if I would continue this and plot in more points, we would basically see this is a sideways parabola. So even though we might not have recognized that up front, once we graph it, we see that it is a sideways parabola. We also know that our calculator really can't graph a sideways parabola unless we do the upper part and lower part separately. So this gives us another way to think of these functions. One thing about graphing these is that we do have kind of a beginning and an end. If this were negative infinity to infinity, yeah, it would be the full sideways parabola. But because we have that kind of beginning and end, a direction is also implied. Sometimes we call that direction orientation. So it's not uncommon to expect some type of an arrow. One's enough, but you can put a couple to indicate what we call orientation. And so that's it. We have graphed our first function in terms of parametrics. Now, if you do this on the calculator, a couple things to remember, because I lost my my ability on the computer to work with the calculator. We lost the license for now. But we're going to have to go into the mode. You're going to see function. You're going to see polar. You're also going to see parametric. And when you try to type in your function, it will give you your x and your y. And you're going to use your t just as the normal variable. When you look at the window, there's going to be a third category. Not only x, max and min and step, y max and min and step, but you also have a t max and min and step. And that's when you're going to put these numbers in. So I'm hoping you can work through the calculator. If not, I can figure out a way to try to show you how to do it, but play with it and try to graph these on a calculator. One neat thing, if you would just maybe only go by 2 and forget to take these out, or take these out on the calculator and graph it, it might just look like a V. All right, so you have to put enough of these points and have the step such that you see enough of the numbers. It would be some fun stuff if we were in class together, but we're not. So that's an example. All right, let's move on to another one. Here we want to graph really the same thing. You know what? I'm going to go a little bit different. I'm going to make this theta. We don't have to. It can still be t. But we usually use the Greek letters when we're dealing with the input of a trig function. So here, the parameter is theta, but it's still going to be just graphing an xy function. So let's see what this might look like. Again, I've got to pick some theta values from 0 to 2 pi. Now here, I'm actually going to do it different. I'm going to have my theta, my x, and my y. And as far as the theta values, I might pick some of the biggies. For like example 0, I'm just going to go to pi over 2, pi, 3 pi over 2, and 2 pi. And it trailed off there, sorry about that. Okay, so there we go. And if I can not quite tell what's happening, I can always fill in the gaps. Well, at 0, the x is going to be the cosine of 0, which is 1, and then multiply it by 2, so you get 2. You put a 0 in here, you're going to get 0. Let's go to pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. Let's go to pi. Cosine of pi is negative 1, so this becomes negative 2. And here it's going to be 0 again. Put a 3 pi over 2 in. Cosine of 3 pi over 2 is 0. Sine of 3 pi over 2 is negative 1. You might have guessed that's going to come back to the original because of the period here is going to be 2 pi. So if these are the only points that I use to try to graph this function, well, you can see that I'm basically just going to be plotting 2, 0. This is kind of where it starts. 2, 0, Then I'm going to plot 0, 2. Then I'm going to plot negative 2, 0. And 0, negative 2. We get this. Now, I could just connect it and think I get a square, but you probably guess that's not really going to happen. So I could go back and put some other nice numbers in. Pi over 4 would be interesting. If I let this be pi over 4, cosine of pi over 4 is radical 2 over 2, times 2 is just going to be radical 2. Same thing here. So you get radical 2, which is about 1.4. So somewhere right in here. Let's go a little further. 1.4, 1.4, right in here. And the same thing is going to be true for some of these. So we're going to get some of these other points. We could do the same thing with pi over 3. Squeeze that in. We could do pi over 6. And we could find all of these other points. And what we would end up seeing, as I find more and more of these, is a circle. Probably not a big surprise. Now, as far as the orientation, it did start right here. So the orientation is going this way. So that's one way we can go ahead and try to graph a set of parametric equations when the parameter represents more of an angle, because we're talking trig functions rather than just a number when we're talking algebraic functions. But both of them eventually lead to a very recognizable type of shape, and that's going to happen quite often. You get good at it, you can just start to notice by looking at it what it should be. One other type of problem, that second type, which would be to write something as a parametric. I'll squeeze that in right here. Let's say we're given y equals x to the 4th plus 1. And our goal is to write this as a set of parametric equations. Well, I have a lot of options. That's the best thing about this. I could simply say x equals t, and then y would be t to the 4th plus 1. That's always one way to go about it. Another option would be to let x be t squared. So if x is t squared, y is going to be t squared plus 1. Actually, not t squared. We would just have to go ahead and figure out what that's going to be. You notice that if x is t squared, that would have to be to the 8th. We could say x is the square root of t. And then y is going to be basically t, we make that substitution, squared plus 1. So, different ways to go about this, but that's not something we tend to do. We don't spend a lot of time on this one, writing this parametrics, right? Because you can always just let x be t and go from there. In just a few minutes, I'm going to produce a quick little video to talk about eliminating parameters and also projectile motion problem.